Okay. Well, good. We're going to move on. We're going to move on to mass spectrometry. Um, well, what's its purpose? We'll start off with why do we use it, its value. Well, primarily to identify unknown compounds. That's what it's really, really good at, is identifying compounds we don't know their identity. We can also use it as a detector. I pointed that out when we were talking about gas chromatography. We could use this as a detector. Go ahead and do our separation in the GC and then detect compounds with it. And if it may be a purpose of identifying compound, if we don't get to identify the compound, it's certainly going to give us some structural information. So it's either going to do an identity for us or it's going to help us in terms of an identity. And then, like I say, as a detector. Like gas chromatography, the list of applications is extremely broad. Some examples, if you wonder about athletes and drug testing, what do they use? They generally use mass spectrometry as the method of analysis. Monitor the breath of patients by an anesthesiologist during surgery. Determine the composition of molecules found in space. Kind of give you a little diversity here. How's that? Determine whether honey is adulterated with corn syrup. Locate oil deposits by measuring petroleum precursors. Monitor fermentation process. Detect dioxins in contaminated fish. Gene damage from environmental causes. Environmental composition or elemental composition of semiconductors. Determine forces are given cobra. Cobra toxins to deaden pain. So racing again and looking at one way or another, doing kind of illegal things. But again, the list is extremely broad, extremely diverse. It is a tremendous technique. Why is it used so broadly? Certainly one of the really... Oh, Ted. Mm-hmm.
So one of the more recent ones they talked about was that they're adding rice syrup to honey, and that there's not yet a method that can detect that. I'm just curious if that's something that has come out since, I don't even remember what that's from.
I don't recall seeing a solution along those lines. Yeah. Adulteration is always a challenge, and that's an interesting one to me. Anytime you, because the goal of the adulterer is always to stay one step ahead of the methodology people, the enforcing people. So it's like vanilla. Vanilla is the most adulterated flavor in the world. There's many times more vanilla sold, pure, authentic vanilla sold, than there are vanilla beans grown throughout the world. And so it's always a challenge. We say, okay, we can use this method, we find this. And then the adulterer says, aha, if I do this, they can't detect it. And it's just a back and forth. Oftentimes there comes a solution, but the solution is extremely tedious, extremely expensive. And so people then oftentimes just don't do it for that reason. But yeah, I'm not aware of that one, whether they've gotten anywhere with it. Well, sure. So sensitivity, again, that's not bad. You don't carry that around a bucket. 10 to the minus 12, 10 to the minus 15 grams of sample. That's adequate. You get the data you want from a small amount of sample. And you do get a great deal of structural information. So identity, hopefully, certainly structural information. And of course, when we're in the laboratory, we want to measure things, quantify things off a liquid chromatograph, off a gas chromatograph, any kind of separation device. It's really good in terms of specificity. We can key in on what we want to measure and exclude everything else. So it really helps us. We don't have to clean up the sample so well. We don't necessarily even have to get separation or resolution. So a tremendously powerful tool. We're going to go through the parts of a mass spectrometer. There's a commonality that all mass spectrometers will contain these parts that we show here. But then each of these parts can be done somewhat differently. So that's where we'll spend our time too, looking at how things are done differently. Well, the mass spectrometer has to operate under a vacuum. we're pretty happy in our lab if we can run around 10 to the minus 7 torr. We had a sample analyzed for us at a company south of the city. They're doing 10 to the minus 10th torr. Now that's remarkable vacuum. The better the vacuum, the better your data. And so that's absolutely required. Because what we're doing up here is we're creating ions, and those ions have to live to go through their separation to be detected. And if there's air in the system, any air in the system, those ions run into air, and they're neutralized. We don't have any ions. So the ion-free, air-free, air-free we can have, the better our sensitivity of the system. So here's our inlet. So one way, like I say, we've got to get a sample into this high vacuum system. That commonly is coming from a gas chromatograph or coming from an LC, so you'll see different methodologies there. But in some cases, you can do what we call a direct inlet. You kind of pull a probe out a little bit, close off the vacuum, pull a probe, put your sample into that, push the probe back in, open the vacuum, and push the sample into the ion beam or the ion source. So we've got to get it in here somewhere. We have an inlet system that we have to manage maintaining that vacuum. The source is what we call source of the ions. We're going to have compounds typically not ionized. We basically want to ionize them. What we're going to do is we're going to do this in different ways. One of the most common is we hit them with high energy. So we bombard our compounds with an electron beam. That electron beam is high energy, 70 electron volts. And that molecule just explodes in all kinds of pieces, neutral, positive, negatively charged ions. And then we take those ions and start separating them by molecular weight. And so we analyze that ion profile. Over here, we detect the ions in real time, and then, of course, data handling and some kind of an output computerized analysis. So like I say, we'll go through this in detail. Electron impact, so this is our ion source. Our most common ion source is electron impact. And that is basically what I said. We're going to go ahead and get our compounds into our source from different ways. I mentioned a direct probe, gas chromatograph, HPLC. We're going to hit it with 70 electron volts. That's a tremendous amount of energy. Most molecules, most chemical bonds are somewhere around 10 electron volts. So I'm putting much more in there than that molecule could possibly stand. Absorbs energy and it just literally explodes. And the deal is there'll be some weak bonds, they readily explode. Some strong bonds, no, they're not going to break apart. So every molecule has some weak spots, some strong spots. And so that molecule, when hit with that energy, will always break into the same pieces, the same fragments. We're going to measure those fragments. Then we're going to go back to libraries and say what molecules have those fragments. So this is kind of what it looks like. We're going to get our sample in here one way or another. Let's say we've got a gas chromatograph coming in. So here comes our analytes eluting from the column. We're just going to have a filament, typically a rubidium filament. We're passing electricity through that. And that rubidium filament will give off electrons. So we've got a constant flow of electrons coming across the path where our compound dilutes. So as our compounds come through here, they get hit by electrons, and they basically, like I say, explode into pieces. So we have, positive fragments, negative and neutral. Generally, we monitor only the positive. We put a negative charge here. The negative charge draws the positive ones out. They're going to come out of here with a velocity. They're going to be flowing very rapidly. And then they enter into the next section of the mass spectrometer. The negative ones get drawn off with the vacuum. They collide with the chamber. They get neutralized. They just disappear. So most of the time, we're looking at the positive. We do have the ability to look at negative ones, and we do in some cases. We don't have the ability to look at neutral ones. We are looking at ions. So normally, we look at just the positive. And that's basically what I was mentioning, neutral, positive, separate, measure them, get a complex bunch of pieces. We start taking all those pieces, all those fragments of that molecule exploding, and we then take that pattern of pieces and go to a computer and have the computer do its matching. What molecules in the library will match to the pieces I find of the molecule I was looking at. And we can then get typically an identification. Not always, but a lot of compounds have been identified. There's an awful lot of compounds in these libraries. Several 100,000 compounds are in there. And so we've got a really good opportunity to do this kind of matching. In terms of kind of terms that we will use, the positive ion of the unfragmented molecule is called the parent ion or the molecular ion. So that molecule may have escaped this largely intact, but it did knock off an electron in the process. So I've got my molecule intact, but it's picked up a positive charge. Basically, it's lost one electron in this whole thing. And so we can get the molecular weight, oftentimes, of our compound. Getting the parent ion or molecular ion gives us molecular weight. That's really helpful. That's really helpful in identification. If you know the molecular weight of the compound you're identifying, life is much, much easier. The other term we use, so parent ion, molecular ion, same thing, our compound with a +1 charge. Our other ion that we talk about and look for is our base peak or our base ion. Same thing. It's the most abundant ion. What's the most abundant fragment that this molecule breaks into? And that's also very, very helpful in terms of identification. So we look at the overall pattern, but some real keys that we like to see. What's the molecular weight? Well, what's the most stable fragment? The one that's present in the largest quantity. The y-axis runs from 0 to 100. So we plot basically the abundance up here, and here we plot mass. So what we're doing is plotting the abundance of the mass of different fragments. And the most abundant fragment is given 100%, then every other fragment is some percentage of that most abundant one. So it's a little different scale than usual, but that's what's been the habit in mass spectrometry. Just, quantify or present everything but in relation to the most abundant fragment. If we would look at a very, very simple spectrum, the spectrum of carbon dioxide. Carbon dioxide has a mass of 34. We've got 2 oxygens, which each oxygen is 16, right? So we got 2 oxygens, 32 plus a 12. We got a mass of 44 for carbon dioxide. And this is the spectrum we'd see. Our base peak is 44. It's the most abundant. Our parent ion is also 44. In this case, the molecular ion is exactly the same as the most abundant one. What do we have, of course? Well, we've got a mass where this energy just knocked off an oxygen molecule. Oh, there it is. And so we've got, of course, CO, oxygen simply, and the carbon, so 12, 18, 28, and 44. Obviously a very, very simple spectrum, a very, very simple molecule. So what are the advantages of this type of ionization? Good fragmentation. That's high energy. Most molecules are going to blow into a number of pieces. You got a bunch of fragments. If you got a bunch of fragments, you got a lot of information. Oh, this ion, that ion, that ion, that ion. And it helps you then have a number of pieces you can build or you can put together the parent compound. If we only had one ion, we wouldn't have much information. Oh, we know it has a mass of 4,800 or something like this. A lot of compounds have that mass. But if I can get some pieces, then I can start understanding where that mass came from. So good fragmentation, meaning a lot of fragments, a lot of information. A disadvantage is you may not see that parent ion. That parent ion may be very fragile. It's just not going to stay together. It's hit by 70 electron volts. One of those bonds is so weak, you just never see the parent. And like I say, we like to know the molecular weight. That's really helpful to us. So when we don't see it, we're a little uncertain about the mass, or at least it's uncomfortable. Let's put it that way. Also, it may lack sensitivity to some extent. We've got a lot of ions, but if there's a lot of pieces, none of those pieces are really in abundance. We've got a tremendous number of little pieces, and so that means we have a little bit less sensitivity to the instrument. So it's really a workhorse. It's what we use 99% of the time in our laboratory, looking at flavor molecules. For that matter, in foods in general, it's by far our most important source of ionization, type of ionization. No molecular weight, no estimate of molecular weight. Here's a compound, ephedrine. And if we looked at that ephedrine, I said these molecules can be very unstable, the parent molecule. And so ephedrine, if we would look at it, what does it give us? It gives us a really, really simple spectrum. Its mass is 165. That whole molecule is 165. We see literally nothing. That could be noise, background. That we see little peaks along the way. And so we look at this and say, we got a mass of 58. 58 can come from a lot of places. And so we'd really like to see that parent ion, or we'd like to see more fragmentation. Yet, like I say, that bond is extremely weak. Got a nice oxygen here, pulling electrons out of that bond, weakening that bond. So in this case, we're not overly happy. We've got too much energy. But so there's ways around that. Let's try a different type of ionization. Chemical ionization is a much more gentle means of ionizing molecules. What we do is we actually get a reagent gas, such as methane, isobutane, or ammonia. And we ionize that gas. So we specifically ionize it. And that now transfers its charge onto the molecules we want to analyze. So we don't pass a bunch of energy. You very gently add a charge onto the molecules we want to measure. And so what happens is we don't see as much fragmentation. That means we got less information to put a molecule together, but we get a molecular weight. 99% of the time we'll get a molecular weight. So at least I know the mass. And if I put the two together, an electron impact where I get the fragments, another one I get the molecular weight, I've got a really good amount of information to get identifications. We use this also in terms of a detector at the end of a gas chromatograph. If I've only got one ion or just a couple ions, they're going to be there in abundance. We'll have a lot of them. I haven't spread the charge out over many things. So I can set my mass spectrometer to maybe look at that 165. And so my mass spectrometer is going to be looking at one ion. It's going to be monitoring throughout a run. And every time I see 165, I think of ephedrine. Okay. And so, but it's a big ion. There's lots of it. It's easy to quantify. So that means I get good sensitivity out of my mass spectrometer. I'm not looking for tons of little pieces. I'm looking for some big peaks. Gives molecular weight, gives me better sensitivity. Disadvantage is, like I say, it doesn't give us much in terms of fragments. So I get a mass at 165. Well, I'd like to know what it broke into. I'd like to know where the weak bonds are, what they are. So there's, pros and cons. One gives good fragmentation. That's nice. Another one doesn't give good fragmentation. Oh, that's nice. It depends on what you're looking for. And this is showing, again, ephedrine run by chemical ionization. And so here's our molecule, 165. Here's a fragment at 58, which is what we saw before. But what do we see? We see its mass over here. Now it's interesting, in chemical ionization, we ionize our analytes by transferring a hydrogen onto them. So I'm adding a proton onto each of my molecules as they come through the mass spectrometer. So this has a mass of 165, but what does my mass spectrometer measure? 156. So it's picked up the 165, 166. So it's picked up one proton, and you'll always see it's +1, +1. We always add one more onto it. So we see more fragments, and we can get an identification of molecular weight, which is what we want. There's all kinds of other methodologies. I don't know if you've ever wandered up to the mass spectrometry laboratory up in biochemistry, but they've just got a host of other ways to do this. Some of the other techniques for ionization, you'll hear people mentioning fast atom bombardment, typically called FAB. High velocity atoms basically bombard a sample in a liquid matrix. Secondary ion mass spectrometry, again, different technique, plasma. We're going to go through some of these, so I guess I won't go through this. We'll talk about them later. One we work with is MALDI, and so again, I'll show you an example here. Electrospray, that's the most common for interfacing with a liquid chromatograph. So that's what we would use. We use our high energy electron ionization. In terms of electrospray, they actually do it very differently. Again, we'll see these. We'll see each of these as examples. So many different ways. MALDI, matrix-assisted laser desorption ionization. Really useful for high molecular weight materials. If you're looking at proteins, peptides, glycoproteins, oligosaccharides, oligonucleotides, they're all in the range that we would like to see. A big protein, no, but a fairly small protein, maybe under 40,000 molecular weight, it really does a nice job. So big proteins, no, but some of your smaller ones, no problem. Really shines in terms of these types of compounds. One of the things we're doing in our laboratory, we're interested in how flavors and proteins interact. Flavoring materials, something like 12,000, 13,000 of them identified for flavor molecules. They're acids, alcohols, ketones, you name the functional group, they've got it. They're chemically reactive molecules, very chemically reactive. You take a nice high protein food, which people want today, I want lots of protein, and you start putting flavor with it. What do we have on the side of the protein? We got, again, all these side chains. We got amine groups hanging off from lysine. We have acid functions, alcohols. Our flavors chemically react with the protein, covalently bond. So some of these proteins will taste very good on day one, but then give them a week to chemically react with the flavor. Pretty quick your flavor starts growing away. And before long, it doesn't taste good at all. And how can we do this? How do we measure this? One of the students is going ahead, isolating pure proteins, adding flavors, and then looking at the protein by mass spectrometry. Looking at beta-lactoglobulin, which is 18,640 or something like that. So he's got a nice peak for the protein. He's got a peak in the mass spectrometer for protein plus a cherry flavor, benzaldehyde, plus another cherry flavor. And so he can look and see flavor molecules being added onto the protein. So it's really a fascinating tool. We couldn't do this before. Ted?
I've seen some flavors that are plated on casing, or they have to do something special to that to protect it from adverse reactions happening.
Some do that. Some choose that route. It's not a good route because the casein is extremely reactive. There will be some shelf life to it. If it's a pure flavor, they got a lot of flavor. And okay, you're going to sacrifice some's going to disappear. If it's in a dry solid, a little tough for that flavor to migrate and attack other ones. Put them in a liquid system, and you're really asking for troubles. It's funny, I spoke on this at IFT, and we talked about protein bars, high protein, and the problems of flavoring them. And for exactly the reason I was saying, you know what happens when you put flavors that really have aldehydes in them? Carbonyl compounds, right? What do carbonyl compounds react with? Maillard reaction, shift space formation, off flavors. And the worst flavors in the world are to add lemon because it's got an aldehyde, citral, cinnamic aldehyde, cinnamon, because it has cinnamic aldehyde as a flavor. And what was the third one? Now, well, that's gone by someplace. But the most common flavors are those. They put them in the bars because people like them, but they put them in the bars and they go away very quickly. So they made the worst possible choice in terms of flavoring. They should pick something like coconut. Coconut flavor comes from very non-reactive flavors. So coconut would last a long time. But they've chosen, like I say, consumer preference rather than the idea that's not going to be there long. It's kind of interesting. And again, we can do this kind of thing because of MALDI, because of the mass spectrometry we have today, which is rather impressive. So what is MALDI? The sample is premixed with a highly absorbing compound, meaning absorbs laser energy. And so you mix your flavor, I shouldn't say your flavor, your sample, whatever it is that you want to analyze. Mix it with an energy absorbing matrix. You put the matrix onto a nice little dot. You put the dot into there in this holder, and you zap it with a laser beam. And that laser beam, 337 nanometers, nitrogen laser, basically explodes it. And so what have we done? We have maybe these are our two analytes, and they're embedded in a matrix. That's our matrix, these little dots. Hit it with this energy, it tends to blow them apart. And so what we do then is we also add a charge to this, and that charge then can be drawn out and measured. So we can measure the fragments, the charges that we get out of these molecules. So I say it's a really fascinating technique. Another way to look at it, here's this matrix, zap it with a laser, we form all kinds of ions, we draw the positive or negative out, but positive ions out, and we separate them by mass, and we get measured over at the detector. There's little fragmentation. These molecules, large molecules, pick up a charge, typically one charge per molecule. And the idea that there's only one charge per molecule makes it pretty easy to estimate the size. If that molecule would pick up one charge, 2, 3, 4, 5 charges, then life gets complicated. But each molecule picks up one electrical charge. And so that, like I say, makes it easier to go ahead and do your measurements. This is an example of a protein that has a mass of 2,466.7. I don't remember what the protein is anymore. How's that? It's a very, very tiny protein. And so that is its mass. And it's a really nice spectrum. Here's from the matrix. Now, if I were adding my flavor, I'd want to see this peak, and maybe a tiny one for benzaldehyde being added to it, or 2 benzaldehydes, or 3, or 4 flavor molecules. Then we'd start understanding a little bit more about the problem of how flavors interact. Fast atom bombardment is really the same thing, but we're using a different means of adding energy. Instead of hitting it with a laser, we hit it with a particle beam. And so those particle beams can be small organic molecules or neutral inert gas. Well, that's the matrix, I'm sorry. We put our sample into glycerol, or 3-nitrobenzene, and that beam is typically argon or xenon. So we bombard our sample with argon or xenon. That gives up the energy. So just different ways to put energy into the system and liberate our molecules. So this is continuation. Yep, transfers its energy to the matrix, to the compound we're measuring. Analyte is ejected off the surface, and then we go ahead and measure those ions that come from the matrix. So here's kind of an example, very similar to MALDI. Here's our atom beam, the argon or xenon. Goes ahead, hits this, high energy. Fragments, really volatilizes some of this. and drags off the analytes that we're interested in to go up and be measured. This is kind of a fun one. DESI and DART are two methodologies that have come about fairly recently. And in this case, for DESI, direct electrospray ionization, what we do is we take a solvent and nitrogen gas, put a very, very high charge on it, and we have our solvent, reagent gas, hit the surface of the sample, and some ions will be formed in the process, and they bounce off, just like playing billiards, right? As angle coming in, as these things explode, they'll also take like this. And here you've got your collector, so you're collecting the ions. And so it's an interesting way to look at something. There's no vacuum here. This is sitting out, and very easy to put your sample under, bombard it, and see what you get out of it. This is an example. I want to know what pesticides are on the surface of that apple. Well, I could go ahead and dump it as a solvent, as we did last time for gas chromatography. I could extract it off, and I could try to find what came off the surface of that apple. Another choice is I could just go ahead and bombard it with my mass spectrometer, look at whatever ion fragments, whatever is busted up and comes off, and I can measure it here. If you ever gone through the airport and been stopped where they take a swab, they go through your luggage or go through whatever, what do you think they're doing? They're taking that swab, they're putting it in a mass spectrometer, and they're looking for, exactly by this technique, components that are used in bomb making. So next time you're at the airport, this is how it's done. How's that? This is a dry interface, so here you don't have a wet solvent, but it's the same type of thing, where you just put a sample in there. It could be a dollar bill. You could be looking for drugs on dollar, well, it wouldn't be dollar, probably $100 bills. Dollar, you wouldn't get much for it. So, okay. So you put $100 bills for there and see if there's cocaine residue or drug residue on it. Just slip it in, it bombards it, and you could measure any fragments. Explosives, yes, whatever. So many, many different ways, but they all work in the same principle in the sense you need to form some kind of ions. You need to either take the analyte intact and put a positive charge on it so you can drag it along and see what it is, or you can hit it with high energy, blow it into pieces and look at the pieces, try and put them together. Depends on what your purpose is. Many different ways. But our first step, yep, that's our first step. We're going to go ahead and form ions. But now we've formed a bunch of ions probably. There's seldom one thing there. There's perhaps many things in your sample. So you're going to have many ions. Now we need to start separating those ions. So we get an ion profile. What is the mass of that ion? Well, was it 2,400 and something in the last one? How do we know? So let's start separating those ions. And for that, we'll use the mass analyzer. So that's the part of the mass spectrometer. There's 4 common types. I'm leaving it open there for a 5th one these days, but okay, 4 common ways to do this. Magnetic sector, quadrupole, ion trap, and time of flight. The oldest, out of curiosity, is the time of flight. That was really one of our first mass spectrometers. Well, we'll come to that later, so I won't go through how it works. But that was displaced over time with the quadrupole. That's cheaper. And now the time of flight has come back to be cheaper, because now we've got good ways of measuring time. We talk about nanoseconds, not a problem. Measure nanoseconds. So it's interesting. That was the first one. That was the big second one. Now it's back to time of flight. When I was a kid, we had a magnetic sector instrument. And I mean that. When I was a kid, for my PhD, I was in charge of the mass spectrometer. I ran this for 4 years. Okay. And at that time, here's your ions. You select out the positive ones, draw them in. There's an electrical charge on this plate, and as these charges meet this electric field, they'll be bent. Then they go through a magnetic field, and depend upon the magnetic force, they'll bend them again. And so what you do is just start off with very weak energy on both of these. And so you'll bend only the lowest energy molecules, the lowest mass around here. And then you keep on increasing energy, you start focusing, okay, the next bigger mass, the next bigger mass, the next bigger mass, to make it actually around here and come into the ion detector. And so at some point, you know, all the masses are being lost up in here and only the small ones. Then you keep on focusing more larger and larger mass through the electric field, magnetic field. It fell into disfavor, so it's a really good detector in terms of its ability to an accuracy. With this type of magnetic sector separation, you can get accurate mass. You get elemental formulas. I can get a formula that says I know exact elemental composition. And so that's really a nice thing. I know what atoms are involved in my molecule. That isn't true of some of our other techniques. So it's what we call a high-resolution instrument. We'll come back to that a little bit later too. But it's big, it's bulky, it's expensive, it's kind of slow. You've got to charge up this magnet and discharge it, and charge it and discharge it back and forth. So it doesn't run real quickly. In our world, we like to maybe do 100 checks here per second. You know, completely scan, you know, 1,000 masses. 1,000 masses 100 times a second. Oh, that takes a little bit of doing. So kind of fell in disfavor. The time of flight is kind of neat in the sense that you can pulse your ion source. So you get your ions, you bombard it, you get the ion formed, it's extracted out. All of the ions, as they're extracted out, have the same energy. And if you remember someplace from physics, kinetic energy is 1/2 mv squared. 1/2 mass times the velocity squared. So as I get, and they all have the same energy, so as I get bigger masses, I have slower flight. Smaller the mass, you know, it goes much faster. So what we do is we measure, we pulse it, form them, and we say how much time does it take? Okay, here's the fast ones, they were small. And then a little bit later, here comes the bigger, the bigger, the bigger, the bigger. So this just keeps on what we call scanning, looking for mass from very low mass to very high mass. As soon as we got all of them down, it zaps it again. And now we got another run and another run where we scan all of the pieces. This quadrupole, there are 4 poles in here. They're basically rods that can accept various electrical charges to it, radio frequencies. And through what I consider magic, because I'm not into electronics, they can put the right charge on these current so they can actually focus. So a mass that comes in here, a fragment, positive fragment that comes in here, it's going to have a velocity in this direction. And by monitoring, controlling the force fields around this, it can allow a molecule of a certain mass, I should say a fragment of a certain mass, to come through. The rest of them are lost, and you can keep on changing this field. So we continuously focus bigger and bigger and bigger masses, and then start all over again. Smaller, bigger, bigger, bigger. So you can repeat that. That is, like I say, is the workhorse. We've got 4 of them down in our laboratory that work on this basis. They're cheap, they're efficient, they work well. They're not high resolution. They will tell you it's a mass 78, but they won't tell you it's 6 carbons and this many hydrogens and no oxygen. It just gives you a mass. It doesn't have good resolution of mass. This is an ion trap. Again, a little specific detector where you will form your ions over here. They come into the right electrical environment, and by, again, controlling the environment, electric field in here, you can focus so you just keep a certain mass in there. You may keep only 78 in here, and everything else goes away. You keep on collecting and building concentration, and then eject it and measure it. So this is kind of neat that the other instruments do it in real time. I've done it, that's what I got. This one, oh, it's coming in, we're going to concentrate, now I'm going to measure it. So it has really good sensitivity to the system. So they each are unique, they all offer certain pros and cons. The time of flight, very flexible. The quadrupole, again, very flexible systems, very reliable systems. And so that's what we see most of. So okay, we've formed our ions. We've separated all those fragments into mass units. Now we're going to measure all of those fragments that we separated and had come to our detector. High energy collisions with the detector will liberate electrons. And so what we do, and I didn't get a diagram of this, I inserted it into it as I was walking over here just before I walked over here, but that's for next year. How's that? What it basically shows is a system where these ions hit the first diode, and the diode, well, so one fragment hits it, the diode gives off 10 new electrons. And then that's focused on another diode here that gives off 10 times more. So 1, 10, 100, 1,000. And it keeps on multiplying, so it's an electron multiplier. So one fragment turns into thousands of fragments, or let's say thousands of charges that we can measure. Tremendously sensitivity. This is what makes mass spectrometry the sensitivity that it has. The idea that we can get a signal and we can multiply, multiply, multiply. In our other methods, for gas chromatography, liquid chromatography, there's no multiplication. You see what you get. If there's a compound coming through, it burns, that's what you got. You can't multiply it. But this system, working with ions, you can multiply the ions and the charge. So it's extremely popular, extremely beneficial type of detector. For data interpretation, if you live this, you get pretty darn good at it. And by that I mean you can look at it and say, oh, mass 58, because there's only a few molecules of mass 58. Well, acetone happens to be one of them. Yeah, it did liberate 15. It lost a methyl group. There's got to be a methyl group, probably hanging out something towards an electron, oxygen molecule. It's going to suck electrons out of it to weaken that bond. So, we maybe have something like this. So, yeah, so you can logically go through this. If you see a compound and it's got a certain molecular weight and it loses 31, you say, oh, that's oxygen. It's an alcohol that's been lost. Oh, I see a 77, 78. Oh, that's a benzene ring. There's an aromatic ring. That's what happens if you live it. If you don't live it, then you depend upon computers to do the searching for you. But it's really, it's an interesting one. You know, you get, the machine spits out its data and it goes through the library and you get some answer. The danger is you put that data in and the machine spits out an answer. So its strength is also its curse or its weakness, because now it's something anybody can operate, anybody can push the button, anybody can get a mass spectrum. I was at the American Chemical Society meeting, sitting in the audience, and a fellow was talking about pineapple wine. And what he had done is he'd extracted the flavor compounds out of pineapple wine, and he'd run them through a gas chromatograph and then into a mass spectrometer. And he started listing. Back in those days, people hadn't done that yet. And so they didn't know all the compounds that were found in foods. They were just thrilled. You know, you sit there through 20 slides of listing chemicals, chemical, chemical, chemical. Boring. But what was fascinating to me is that he started listing them, and he said, okay, and here's methanol, and here's some butanol compound. And here we've got, okay, the butanol, and after that comes acetaldehyde, and goes, and then butanol, and I'm sitting there thinking, wait a minute, he listed butanol twice. Normal butanol, you know, there's not isomers of that. How on heck do you get a peak here from your gas chromatograph and then a peak out here for butanol? And some of the things in between didn't make sense. So kind of at the end I said, pardon me, sir, how can you have two forms of butanol? How can you have two identifications of that when they're separated? And your order typically is what comes out of a gas chromatograph, and it's impossible to have that order because they're separated in terms of volatility. He said, well, that's what the machine said. That's what the computer said, right? And that's the danger of it. When it gets so simple that you can push a button without any thinking, without any learning, and you'll make a mistake. So the computer isn't fallible. It gives you the best choice as it figures it out. Ted?
You ever see stuff come through with a C13, so going off from what you'd expect?
You will see always, yes, the normal C13 distribution. If you get a 78, you get, 79 from, as a small 1% or something like that peak. And it comes from C13 isotopes. And of course, in your research, oftentimes you'll put C13 into a sugar molecule, for example, all C13s. Then you want to react it with something. Then you look at the product and say, oh, look, where's the C13? How many? Oh, they came from the sugar. So you start determining pathways, chemical reaction pathways or metabolic pathways in plants by looking at the isotope abundance. Yeah. Again, that's a very, very useful tool. Plus, the danger is when it does it for you, that you're not thinking about it and you're going to make mistakes. And that can be extremely expensive. It can be extremely dangerous. You really want to be careful about these things. High resolution, we got another minute. Low resolution just says, as I said, it'll just give you a mass. But if we're using a high resolution, it'll actually give you elemental formula. You can have a mass here, 28.005. That can only come from two nitrogens. It can come from no other source of combination. It can't come from 2 carbons plus some hydrogen or something. It has to come from a certain elemental composition. Very, very powerful tool. Once you know elemental composition, it doesn't tell you how they're put together, but it's really another good start. Well, this was actually the story where I was supposed to tell you about, how you can make a mistake by trusting the machine. And that's true of any machine. You don't take a number that any machine gives you without looking at it, without thinking about it. So I don't care what it is. They're a black box as far as I'm concerned, and you validate the information it gives you. You could lose your job. You could lose much more than that if you would say something, oh, that's safe, no problem at all. And in fact, it contains benzene or something that you misidentified. So anyway, we'll call it quits here, and we'll try to finish this up, probably only half the lecture. But don't worry, your boss is going to take over for the last half. Okay, have a good one.